Morning, everyone present. It gives me immense pleasure to extend a warm welcome to all participants to the day 2 of expert lecture session organized under the Gyan course entitled Modeling and Management of Inverter Based Resources Integrated Electric Grid. We now begin with lecture 1 of today's session. We are honored to have with a distinguished speaker, Professor Sukumar Kamalasadan sir, who will be delivering an insightful lecture on optimal power flow modeling of electric grid for electric transmission and distribution system. Professor Kamala Sadan is a renowned expert in the field of power systems and electric grid modeling, and we are privileged to have him share his deep knowledge and valuable perspectives with us. So without further delay, I now invite Professor Sukumar Kamala Sadan sir to begin the lecture. Sir, please.
Thank you. Good morning. We have going to have some fun, wonderful time with the new rather a topic that is a topic that is evolved from yesterday's lecture. Yesterday we talked about power system modeling, right? Device level modeling of electric power grid, and then we talked about power flow, right? Remember power flow. Power flow models are used to study the electric grid power flowing from point A to point B by calculating the voltages at different points on the electric grid and then finding out how much power will flow from point A to point B. And then these power flow models that we studied yesterday, we studied the power flow models for electric transmission system and then electric distribution system. So these are the things which we studied yesterday. So power flow is basically used to find out if you are given a load on an electric grid, what would be the power transfer flowing through each line or each branch of electric grid, power network, and how much will be the power at each point, power meaning active power mainly, also reactive power, and how much will be the voltage at each point. This is what we call it as a power flow. So there are techniques or method that we use using mathematical models to study the power flow, right? So what we did yesterday was giving you an idea about how these models can be developed for studying power flow. What we're going to do today is extending that knowledge to do something what we called as optimal power flow. Okay, so first we will need to understand what's the difference between a power flow and the optimal power. So optimal power flow is mainly used to obviously manage power flowing from point A to point B, considering the cost. Okay, what do you mean by cost? Cost doesn't necessarily mean money. Cost can be some value. For example, improving voltage on an electric grid throughout as a voltage profile can be considered as a cost. Improving stability margins of electric grid to improve, to make sure that system is more stable can be considered as a cost. So anything that actually gives value to electric grid management can be considered as cost. So this is done through a mathematical method called optimization. Okay, so what we're going to do today is to talk about how the optimal power flows are formulated and how do you compare that with the power flow, how that power flow becomes an optimal power flow, what is the value of this optimal power flow, and what are the techniques we use to perform optimal power flow. It's a basic theme of today's topic. So what we will learn at the end of the day today, hopefully, we know how to do the power flowing from point A to point B. What are the variables, voltages, angle of voltages, active power, reactive power, which we studied yesterday. Today, by end of the day, today you will also learn how to make sure this power flowing from point A to point B is considering cost, economical. Excellent, in a simple sense. All right, so what we do is we will just jump on to some basics. Now, if you look at the IBR integration on optimal power flow, again we keep on talking about IBR integration because that is the so this optimal power flow is currently performed on the electric grid. Okay, and there are electric grids, I think probably in India too. I'm pretty sure there will be, but there are electric grid in the US which runs on optimal power flow in operation. Meaning every 10 minutes or every 10 seconds or every 15 minutes, this optimal power flow is run to optimally manage the electric grid. So there are optimal power flow which has been implemented on the electric grid currently. Now, what is an optimal power flow implementation? How that needs to be expanded, how that affects the IBR integration is the topic of interest for our course, GAN course. So we will have two tasks. We'll have to first understand the optimal power flow methods and techniques, how it's been implemented. Then we also need to understand what happens if IBR comes into place. How do we really need to enhance the optimal power flow? How do we include IBR in the mix? What are the challenges associated with that? Those kind of things. So we'll try to touch upon, you cannot touch upon all the different aspects of it, but we'll give you some flavor on few things that how we do that. So if you are going to look at IBR, you will be seeing mainly the effect of IBR on the optimal power flow management, including optimizing with respect to some criteria, which is called resiliency and reliability of electric grid, can improve some of the biggest disasters that can happen or that has happened in the past, including IBR, with IBR in the mix, such as natural disasters, emergence of low type, proliferation of measurement and control devices, high penetration of DVR. So these are something that actually gives more value to this optimal power flow topic, which has been done in the past because of the challenges of the electric grid that is coming in future. So, efficient load flow method that can solve power grid with DER computationally efficient. Can we improve that computational efficiency? The time dependent effects on those dynamic changes. These are the things that we actually talked about yesterday. So if you are going to look at what is changing, we already talked about changing parts are on the electric grid. Our first change is on power distribution system, and that power distribution system was not having a lot of generating sources on the power distribution system. Remember that when we did a distribution power flow, what we did, how many sources we had? If you did a forward backward sweep of distribution power flow, how many sources we had? How many sources we added? We had one source, and then so that is actually the existing power distribution system. So what is going to happen if you have a lot of photovoltaics connected to it? There will be multiple sources. Okay, such distribution system, power distribution system with multiple sources is now going to be talked as active based power distributions. What do you mean by active? Meaning there are generating sources connected to it. And we also talked about a word called prosumer. Remember, what is a prosumer? It's a consumer and a producer, right? Both together, which means generating power as well as heat. So then the power distribution system will be active. So for example, DER, PV installation, EVs, all those things which is on the power distribution network, make that as an active power distribution system, right? And then you also have devices which are active coming at the last point of the power distribution network. So this last point on the network, like as if you have homes and then connected PVs on that, that is generally called as grid edge. Okay, so you will use this, you will see these terms coming in your life. So I wanted to also touch base with some of the jargons and what is coming in here and why we want. What do you mean by grid edge? Edge of the grid, basically. So these grid edge challenges are also plenty. What are the challenge? One challenge associated with grid edge, which we talked about it yesterday. We didn't say it's edge, but we talked about one of the challenge with respect to power distribution system. Voltage start going down from the substation to the what happens to the voltage at the edge? Last point, the lowest, right? So this is a known challenge. So if you have a photovoltaic on the rooftop and you are producing power, what happens to the voltage on that point? Voltage will go up because you're pushing power to it. So voltage start increasing. So is that photovoltaic coming on the rooftop at the edge of the electric grid is a blessing? Yeah, it could be a blessing if a voltage. However, what happens if this photovoltaic is producing and consuming? I mean, producing high and producing low, producing high and low. What happens to that? It will become very problematic with respect to the voltage. So grid edge management is also critical. So now we know with this background what is optimal power flow. Optimal power flow is actually will be able to do with DER multiple things. First, it can save money. It can save electric grid from disaster, which is it will save lives, or it can obviously integrate more renewables into the electric grid. Okay. So this is how the optimal power flow generally can work. So what will be the output of an optimal power flow? What will be the output of a power flow or optimal power flow? Output of this optimal power flow and power flow, what you run the power flow, will be a bunch of set points or reference points that is going onto the devices in the field. Okay, and what does that device do? The devices will be able to generate power based on that set points. So for example, let's assume that you have a PV farm sitting there with battery. You can send a set point to the PV farm and battery and say that, hey, economically or value wise, you should generate 3.3 megawatt. So then there will be a control system that is working on that PV farm to generate 3.3 megawatt. So this reference points, which is coming out from the optimal power flow, can be used to set a given reference to devices, for example, capacitor, and faster changes to devices, for example, lobes, to devices like example battery, and devices such as electric vehicles or photovoltaics. And at the same time, you can also send the signal to the devices like these. What are these devices? We talked about it yesterday. What is this? Huh? What is the symbol? Huh? Transformer. Okay. And what is the line that arrow means? Huh? Yeah, variable transformer or tapped transformer. So you have a tap from the transformer, and we talked about tapped transformer, right? So these tapped transformers can be voltage regulator or the transformer at the side. So now what we are doing is we can send set point to these devices and have the device manage using controllers to take care of the set point. So these devices which are already there on the electric grid, which is controllable, are generally called legacy devices or legacy electric grid, okay, which is already there. These are the ones which is going to be new, or what we generally called as smart devices or newer devices added to the electric grid. So this operation and control happens based on this whole loop, sending set points, feeding the set points back, and then doing optimization based on that. Are you following? Okay. So, the goal of this optimal power flow is basically to generate set points to these devices and that coordinate that set points. So what are the learning objectives? The learning fundamentals of power flow and optimal power flow, learning how to cast distribution system applications and optimization problem, learning how to model OPF problems, and we will also do maybe one one hands-on tutorial or test after this lecture today, combining two hands-on two problems that we said we will solve yesterday, which is on power flow, and one maybe a code-based problem in MATLAB to solve optimal power flow. Okay. So how do you cast an optimal power flow problem? There is a term that I use some terms which is coming from the methods in optimal power flow. One term is cast. Casting means formulating and developing. Okay, so cast an optimal power flow problem means you're formulating an optimal power flow problem. So optimal power flow problem is based on a framework of optimization. Okay? How many of you heard of optimization? The word optimization. How many of you heard of a mathematical model of an optimization or seen a mathematical model of an optimization? 2, 3. Okay. All right. So I need to discuss a mathematical model of an optimization. So what is an optimization problem? Do you know? It's a difference between an optimization and control.
Depending on the object, I think they are either minimizing or maximizing. Like if it is profit function, we need to maximize it. If it is a cost function, we have to minimize.
Very good. Excellent. That is an optimization. Minimizing or maximizing. So why do you want to minimize something? Okay. I know I have to reach here. And I'm here. I can go directly here. Suppose I'm going here, and that's a minimizing problem. I can go here all the way here, not go there. That's minimizing, right? Why do I need to minimize? Why cannot I go directly to the problem? So in other words, I'll give you a set point 3 and I want to go to 3. I can go to 3 using a controller, right? By an optimizer, I will not go to 3, I'll go to some other point, right? Why cannot I go to 3? Why do I need to go only to minimize? Why do I need to minimize a problem? The reason for minimizing a problem is that I cannot get exact solution. That is why I'm minimizing a problem. Now the next question, why do I am not getting an exact solution? So the reason for not getting an exact solution is that there will be multiple variables or multiple constraints or multiple decisions that I have to make to reach at that point. All those decisions may or may not be contradictory. So if it is completely contradictory, I will not be able to go there at all. If it is better, I may be able to halfway go through that point. So for example, I have a point that I need to go, but there is no road there. It's hard to go there. If it is possible for me to get rid of all the, if it is forest area, get rid of all the stuff, I may reach there. But if it's not possible, what will I do? I'll not go there. I'll stop somewhere in between. So the challenge on optimization problem or whatever, whenever I use an optimization problem, you will have to find out there is many variables that you are contradicting to reach at that solution. If there is no contradiction, obviously you can do that with help of control or other device. You understand the problem, right? So optimization is only used on those conditions. You cannot use an or you don't need to use an optimization. So you have to understand the need. You cannot use an optimization problem for solving something that can be solvable, that can be castable or able to formulate. Okay? So this is what an optimization means. Now, how do you do an optimization mathematically? Develop an optimization problem. You develop an optimization problem based on a function that you think will let you go to your final destination point. Okay, that function is generally called objective of what you want to achieve. That objective function is any function that is dependent upon two variables. One is the u. Okay, in control theory, this u is generally called control controller output or the input to the plant. Okay, that is generally what we call it as U. Controller out or input to the plant. In the optimization world, this U is generally called decision variable. Okay, making a decision. Same thing, but called as a decision variable. So it depends on the decision variable U, and it also depends on X. What is X? You understand this model of state space, right? Have you done one course in control theory? Anybody has done a course in signals and systems? Signals, systems, okay. Control theory. Do you understand state space? Have you heard of state space model? What's the state space model with respect to a state variable X and a control input U? How do you represent a state space model? Have you heard of this equation? X dot is equal to AX plus BU. Okay, so the input U goes into the plant, and the plant output is basically the state variables. And so similarly, in here, the state variables are represented as X. Okay, in the X dot equal to AX plus BU, what is U? Input variable, right? What is X? State variable, and the output is represented as Y. Easy. So Y equal to BX plus CX plus DU, that kind of a form which you have. Now in the optimization world, state variables X and decision variable is represented as U. And the function that we are going to minimize or maximize is represented as a function of state and the input. Okay. Now, many times when you do optimization, you want to go to one specific place or location, you will have a path that you can go through. Okay? This path, there are several paths I can go through to that point. The combination of these paths in a space, we call it search space or a state space. In the state space variable, we call it state space, called a search space for the area. So that area you need to be defined. If you don't define that area, what will happen? Well, you may be able to transfer from any place. Okay, so the definition of that area is important. Okay, and that definition of area is the first thing that you need to go look into. But second thing that you need to look into is that is there any problem for me to go from point A to point B? Any challenge? Suppose this path is not possible to traverse or go through. Okay, I'll have to avoid that path, right? So that is what in general called as constraint or conditions. Okay, so any optimization problem, if you have a space, you also have some constraint. Okay, if you have a space, how do you make sure that I'm not going everywhere? I'm going confined to this. That is bounded by these constraints. So that's called the boundary. So you need to have a boundary, you need to have a constraints in that along with that boundary. And that general process is what we call it as constraint-based optimization or constrained optimization. So any problem that is mathematical can be just optimization. But that problem, suppose you cast it into a physical device or a physical power grid, that optimization problem will become constrained optimization. Okay, so every time you will have an objective functions and you have some constraints. Mathematically, these constraints are divided into two parts. One part are the constraints that can be equated. Okay, such constraints are called equality constraints, which can be equated. Some of the constraints you cannot equate. Some of the constraints you can say, oh, you don't have to go higher. It can be same that number or lower. Such constraints are called inequality constraints. So optimization problem has three main parts. One, an objective function. Second, constraint divided into two types, equality constraint and inequality constraint. So can you tell me an example of equality constraint with respect to power flow? We did study power flow yesterday. What are the main two equations in power flow? Power balance equation. So what is a power balance equation? Is that equality? That is equality. So power balance equation can be considered as an equality constraint. How do you write a power balance equation in the form of an equality constraint? So you can say that power generated is equal to power consumed by the load Power consumed by the load is a great thing if it is the same, but you also have losses. So you say power consumed by the load plus losses. How do you cast that same problem with the PV farms? Is equal to the load power and the loss power. So that same thing which you can. What happens if this PV farm power is not a number? It's going up and down. So the PV power can be plus or PV can be minus, right? I mean, if it is, let's assume that it is a net load. You remember the net load we talked. What is a net load? PV plus load. If the load is higher than the PV, it is positive. If the PV is higher than the load, it is negative, depending upon the sign. Sign convention, positive means absorption and negative means, you're pushing. So this can be positive or negative. So what will you do? Well, then you may have to cast it into two equality constraints or one inequality constraint divided into two parts. You may have to cast like that. So this is what our engineers do. We don't do anything related to a lot of mathematics. We borrow mathematics from, like I said yesterday, from different places. But we smartly try to cast or form the problem so that we can solve the problem to get a physical outcome. So that's basically the idea. So are you comfortable with this now? Okay. So we have objective function. We have constraints divided into equality constraint and inequality. So any questions? Make sense so far? Okay. So what is that optimal power operation objective? The optimal point of operation satisfies the network physical constraint and the fundamental rules of the power flow. So now we wanted to go with the optimization problem casting onto power flow. So if the optimization problem, when you cast, I use the word cast all the time. You know what that means, right? When you optimization problem coming to power flow, it is generally called optimal power flow. Okay. So what are the criteria that needs to be satisfied if the optimization has to go into the power flow? Criteria that needs to be satisfied, the optimal point of operation should satisfy the network physical constraints, right? What is a network physical constraint? Can you tell me one network physical constraint? What's a network? Lines. Let's connect. That's network. What is a constraint of a network on a line? Any constraints? No constraints. If you push the power to that network, the network should be able to take that power. If the current is very high, what happens to that network? The network will not be able to. So you have a limit at which the power can be pushed through the network. That network power that can be pushed to the network limit is a constraint. It's a higher upper bound limit for the mathematical problem. That constraint is generally called thermal constraints, which means with the help that power that is going through the network should not go as a heat. So that's basically what we consider thermal constraint. So is that the only constraint on the network? May not be the only constraint. There could be constraints with respect to voltages on a points which is on the network. So that voltage constraint needs to be honored. So if you want to look at optimization problem mathematically, and if you want to convert that into optimal power flow, you have to take care of physical constraints on the mathematical optimization problem. That is where our brain comes, and that is what ChatGPT cannot do or any other thing cannot do, like we were discussing yesterday. That's the place you will need to think while you are working on a problem. So the goal for an engineer should be, I believe, is to make sure these mathematical methods that you are trying to work on has some physical sense and can be applied onto the physical sense. Whether it is a computer science or whether it is any other place, you must think that as a physical sense. That's basically the objective of the smart grid. Many times I have seen people working on optimization problem because that is seen to be very interesting. So for example, there are variable optimization methods utilizing soft computing architecture. For one of the soft computing methods that you can see can you name a soft computing method that can be applied for optimization? Hmm? There are things like swarm optimization, particle swarm optimization. These are variable optimization. Those variable optimization do not have any physical condition. You do just number in, number out, and that is what you need to talk about. So if you wanted to pass that into the operation of the power grid, should make sure it's take care of the physical constraints in the powerful network, and the objective to determine the state control variable to minimize the total condition for the electric. All right. That being said, we'll talk about some of the real physical things. Objective function for a now we will talk about optimal power flow. Okay, so there will be a phrase or a short name that comes all the time from now on called OPF. OPF means optimal power flow. Optimal power flow, is this optimization? Yes. Is it power flow? Yes. Is it a combination of optimization power flow? Yes. So you got to remember, power flow comes from physical side, which is like a real system. Optimization from mathematical side, we are kind of merging them together into one. So optimal power flow objective function, OPF objective function, can be loss minimization. One of the objective function that is done in the electric distribution grid on power flow is to minimize the losses. Okay. So what do you mean by minimizing the losses? Everybody understand minimizing the losses? Why there is a value in minimizing the losses? What is the value in minimizing the losses? Huh? Yeah, it is cost optimized. What is the value in minimizing the losses? The losses goes down on electric grid, what happens? Your energy bill should go down because ideally should go down, and the electric utility will be getting power generated in a less power generated because losses go down. If so, losses, I don't know what's the number here, 8%, 10%, something like that. If you go to 5%, 4.5%, 4%, these are the good number which we talk about with respect to the losses. So, in some countries, losses goes up to 10%, 15%, 20%, including if you include the theft along with the losses, then it's going to be a very high number. But I think we are in India, the theft factor is very less now, I guess. But so that's what I heard. It's improving with respect to some smart technologies, and the loss is hovering around 8 to 10% or something like that. So reducing the losses can be one of the objectives. What is another objective that you can call that as? Conserving voltage. Have you heard of conserving voltage and reducing the voltage? This is something that is done in power distribution system network. What do you mean by conserving voltage reduction? Which means that the voltage that is being throughout on the optimal on the electric distribution system is conserved. Okay, what do you mean by conserving voltage? So the voltage normally on the electric distribution system has to be between a band, which is 0.95 to 1.05. Between 1.95 and 1.05, what will be your best voltage? 1.05 or 0.95? Huh? One is perfect because you like one, but you have a band, you can go from 1.05 to 0.95, right? So where do you operate? You operate on the boundary of 0.95 to get the better bang for the buck, meaning losses, or you operate at 1.05 to you have the room. Yes, you have to operate a little lower, and if you operate the voltage lower, that's the best way that you can maintain. So that doesn't mean you cannot hit to 0.95 because there's a change associated with it. Voltage is generally going to go lower because of the type of the loads connected to it. So you got to lift and at the same time not lift too much, but you have to leave it like that is a tough task. Actually, mathematically to solve that problem is also very difficult because that problem is not feasible, we call it. Oh, there is another term which comes in from mathematics in optimization, what we call it as feasibility. Okay, I will tell you 2 minutes story about feasibility, then we'll come back. There are two types of feasibility. Generally, feasibility means, what do you mean by feasibility? What comes in your mind when somebody says feasible or not feasible?
Whatever we are doing, whether it is possible or
Possible. What do you mean by possible?
can be done or not.
What do you mean by it can be done or not?
Constants are better.
You can actually, there are different level in your feasibility. First level of feasibility, can you implement this or not? Can you, say, oh, is this whole thing what you did, is that feasible or not? Because, okay, you made all these things. Is that going to be in real life? Can you make a box out of it? If you can't make a box, the applied engineers will say, oh, it's useless. That's not. That's feasibility. Is there any other feasibility? Can you develop this or not? It's a feasibility, right? It's a problem, so it's called feasibility, right? So can you develop it? That's what you're talking about, whether possible or not. Get it done is something very vague. Can we get it done in the box or get it done in the math or get it done somewhere, so that is, you will not want to use. So feasibility spans. So feasibility of an optimization problem is exactly the same. Optimization feasibility is whether mathematically you can solve the problem or cast the form or form the problem. Power flow feasibility means, oh, I cast the problem, I solve it. Is that really good? It's all solved, but the voltage is 0.45. And say, it is not feasible. You did solve, the method is there, nothing is breaking, and the software is working, but it's not feasible to implement. So feasibility of a problem, when we talk about those two different aspects, mathematical feasibility as well as implementation, whether it's feasible or not. So having said that, I'll talk about minimizing PV curtailment. Have you heard of the word curtailment? Maybe grounding here and math, I'll go a little faster because maybe you can catch. What do you mean by curtail? Reduce? Remove, cut. Okay. Cut is a very nice word for curtailment. But cut, when do you cut? If somebody is behaving bad, you cut. Okay? In electric grid, whoever is behaving bad and you cut, you call it protection. Basically, protection is not to take care of the bad folks. Protection is to take care of the good things in the electric grid, cutting the bad one out. That is basically the property of protection. So if somebody is behaving bad, you cut. What happens if you are behaving good? Will you cut? Generally, you don't cut. Curtailment means behaving good photovoltaics, you cut. That is curtailing. Okay, what do you mean by that? So let's assume that the photovoltaics are allowed to supply maximum power from the solar farm. Maximum power is have you heard of maximum power tracking things there. So maximum power comes from the photovoltaic. Now let's this maximum power comes from the photovoltaic and you are allowed to get it on the electric grid. What happens if this maximum power at some point of time increases in voltage to above 1.05? Normal operating condition. PV is doing good job. PV is not doing anything bad. It's coming with you and it's coming to you. But we know that if that comes to the electric grid is messed up. You know what will you do now? You cut. Will you cut it to zero? No, you may not cut it to zero. You may cut it to a level that the voltage is balanced. This is curtailment. So curtailment is not when you behave bad, what is a word that you talk when you behave bad and you want to cut it? Instead of curtailment, you call it islanding. This is the word that you use for behaving bad and cutting. So behaving good. I just wanted to say the difference between curtailing and islanding, and curtailing and cutting. So what do you mean by cutting? Cutting can be good or bad. I mean, you cut. That's basically good. So you curtailing the photovoltaics is actually not good for us. Why? Because we are not able to gather that power. The power is lost. Curtailing the photovoltaic we are doing because we are forced. So now the question is, can you minimize curtailing? Can be done with the help of good optimization if you do. If you minimize curtailing, what happens? That's basically our value. Value is not just money, but it's also sustainability, carbon decarbonization, the 3D that we talked about. All those things comes with the help of value. So that's what. So now equality constraint, you have power flow equations, equality device models, state related constraints. We talked about this device modeling. Equality constraints means that you are going to make sure that input is equal to output. Okay. For example, there is in power electronics world we talk about output power is equal to input. DC is equal to AC, 1-to-1 ratio. There is no Nothing except for the switch losses. We try to neglect it and then make it small or some. That is an equality constraint. You can make sure that the DC power is equal to 1-to-1 ratio to the AC power without having to make sure that you cut. There also that's a waveform cut. It is not a real power curtailing. So that is actually can be considered as a constraint, which is an equality constraint. You can include it. This will normally come if you are trying to do what we call it as DC power grid. DC power grid in a small sense with power electronic devices not utilizing the higher voltage level is called DC microgrid or some kind of a device where you have a DC network. If you go into the higher devices, it is called high voltage DC grid, which is generally classified as HVDC, those kinds of. So the DC network can be integrated to the AC network with the help of this, with the optimization. You optimize basically DC side and the AC side, and you can put that equality constraint there, right? So any things can be casted in the form of mathematically in the form of an electric grid design. So that's equality. Inequality constraint, network operational limit, voltage bounds, capacity of DERs. Okay, so now with that being said, now we are going to go a little bit denser. Okay, we are going into some math related aspects, but I will try to relate as much as I can with respect to the physical side. We saw this picture before. Everybody remember this picture? What is this picture? This picture is a one line representation of an electric distribution grid. Very nice. And this point of that electric distribution grid is a source that is connected to bus number I that can be considered as a substation. Remember, we did a substation, L03, there is a voltage drop, and this drawing which we did, this is exactly the same drawing. After this substation, you have a LTC. Everybody know LTC? Remember LTC? We talked about the whole story about LTC. Then you connect it to another bus, and after that you connect it to a bus A, where you have a load connected at a capacitor bank. Then you connect it to bus M. There is a DR connected load, and there is a bus, KL, DR connected and load. All these buses can be considered as trunk of the tree, which is three phase. These buses are considered as laterals. Remember we talked about yesterday laterals, and that can be two phase or single phase or things like that. So this is a very small, nice representation of a electric distribution system. We will try to utilize this for our math problem. We'll try to utilize this for our simulation. When you do MATLAB simulation, we'll just try to study in this whole. So if you are looking at this problem, we use this problem to done power flow. Now we are casting the same thing in the form of optimal power flow. Good. You understand this, you understand this, you understand this. What is this? This is the voltage angle of the voltage. This is basically the voltage magnitude and voltage angle that can be used as a state variable, and the current and current angle that can be used as a branch. Okay. All right. So once we do that, now we start looking at some of the other variables. So one, you can have optimal tap setting for the voltage regulator, tap positions, decision on the status of the tap, DER, real power dispatch from the DER, reactive power dispatch from the DER. So this is basically your considered as decision variables. Remember what is a decision variable? It's a variable that you are going to give as an input to the device. So optimization is done, optimal power flow is solved, you take the output of the optimal power flow, you give that input to the device. That input to the device is basically from the optimization side, we call it decision variable. For the device side, it is a set point. That set point is used by the controller of the device and make sure that I reach the set point. So that's the relationship between optimization and the device level control. So the device level control will take that set point, and the optimization world, we don't say set point, we call decision variable. And then how many decision variable you can generate? It's up to you. Any decision variable. So centrally you can look at the whole grid optimization, and then I can say, 7 different decision variable and give it to the How you give? Through a communication network or some channel, you give it to the devices in the field. So some of the decision variable include on-off status of a capacitor bank. You can say, hey, capacitor bank, you need to be turned on at a given point of time. You do this optimization on a time basis, snapshot, okay? And every 10 minutes, every 15 minutes you run, so you get this output and then you give that information. DER, real power dispatch of the DER. Oh, so this real power dispatch of the DER, will there be a curtailment? Yes, there could be a curtailment because we are making sure that the system is optimized. Reactive power dispatch of the, and then you can also see AIJ. What is AIJ? What is A? Tap ratio. Okay, we talked about it. Tap ratio. What does the tap ratio do? It changes the taps. When it changes the taps, what happens to the output of the voltage? Changes also. Good. All right. So now we talk about. So we learned the objective function. We also learned the some of the constraints. Now, some of the decision variable. Now we talk about the constraints. There are two types of constraints. One constraint is equality constraint. Examples of equality constraint. Voltage drop equation is an equality constraint. Voltage relationship between a transformer is an equality constraint. Power flowing through the branches is an equality constraint. So every power for every point should be related to voltage times current is an equality constraint. For this network, you have Sij, Sjk, Skl, and Skm. Power flowing. You also have Vj, Vk, Vj, Vk, Vj, Vi for this, and Vj, Vk for this, Vk, Vl for this, Vk, Vm. So if you make it as a generic mathematical algorithm, you can start from scanning the power network for all the nodes and then writing this equation for all the nodes, which is a pretty interesting deal, but it is less challenging because you have to increase the, remember we want to write this on an electric grid, right? Why you want to do this on electric grid? Models needs to be scalable. Remember we talked about it. Then only you can say that it really works in the real life. So that's one of the things that you can see as a challenge. I talk about some other constraints. So power balance equations in the network, you can write the power balance equation in the network like this. Sjk minus the drop is equal to Skl plus Skm plus Slk minus capacitor. So you can actually look at the power flowing, the incoming power should be outgoing power and this capacitor power and the load. Are you following? KCL, current coming in is equal to current going out. So current coming in is this current, this current, this current, and that current. You don't care about these two because you are only considering KCL on that bus. But what happens if you consider KCL on this bus? Going in is equal to going out plus going out, right? I'm talking about algebraic. This is negative, then when you put negative, that same thing here, current coming in, going out, going out. So there are three different equations that is representing. I'm not going to each one of the variable in the equation. You understand, right? In the form of a power. Good. Are you following? Okay. Now we move on to inequality constraints. Inequality constraint comes in two forms. One form is, we call it double inequality, which is voltage, for example, has to be between minimum and maximum. Okay. This inequality is generally called box constraints. What do you mean by box constraints? You are putting in a box. You are actually not saying that it has to be higher or lower. You are putting them in a bucket and say, hey, stay here. Don't go this way or don't go that way. That's called box constraints. You see box to several of them. Oh, how many boxes are there? Depending upon how many buses are there. You have 5 buses and 5 box constraints. You see, most of the box constraints are based on voltage. Following? If I'm going a little faster, you got to pull me down, okay? If you're not understanding. I think in this section, you're okay. I don't know what. Are you following? Yes? Board? Math? These ones are not box constraint. Mainly you'll see thermal limits. Okay, rated value of the current on the line should be, the actual value of the current on the line should be less than or equal to the rated value of the current on the line. That's the thermal. I'm giving you a scope-based method. You may ask the question, can I include other things? Yeah, you can include anything you want, but you need to know what are each one means so you can add more things later. So this is just as a example-based discussion. Okay, what do we do with DERs, inverters? Remember our topic on GAN is IBR integration 2. So what do you do with the inverters on optimal power flow? We did inverter on the power flow basically. You talked about what you do on the inverter based resources. On the power flow, what do you do inverter based resources on the optimal power flow? Again, we worry only about inverters. You don't worry about inverter based resources. Instead, you worry about inverters. And you assume that the inverter based resources behind the inverter is trying to push maximum power as possible. So what you do is you try to develop an inverter decision equation based on smart inverter. And what is a smart inverter equation that you can derive? You can say that power from the DER, the power from the DER is set by power point tracking, pushing the power to the electric grid. Reactive power from the DER is changed based on the active power and the capacity of the inverter. If the capacity of the inverter is 7 MVA and the active power which you are pushing through this inverter is only 250 kW, well, you will get free reactive power. Why it is free? We talked about the story of being free. Why it is free? No inductor, no capacitor. It is only the difference between the angle on the voltage and angle of the current, basically. And that's what we consume from the reactive power controllable DER, and decision variable is this set point. So there is a big discussion that happens, I gathered when I was in Bangalore, that in India, which inverters needs to be smart and which inverter should not be smart. And how do you control the reactive power from the inverter? I mean, there is some discussions going on. So you could use this optimization method to set how much reactive power should come from the inverter at a given point in a power grid. And that's sacrificing the real power. So that is a trade-off. So what you have to find out to see. So for example, in some places you need to improve the voltage, and you are doing in a maximum power point tracking, like you said. You have a curtailment problem, you have to cut it, or if you are not cutting it, you have to improve the voltage so that you can push the power through. So you may try to say, hey, I got this P down, then I make Q up, and where is my good number for P and Q such that I can get the maximum P at the same time, improve the voltage as the same. That's something. And once you do that, obviously, and now there is something called oversizing the inverter. So what they do is that 250. So what we did in a field in US, we had a battery with 250 kW with 750 kWh, 3-hour duration battery, 250 kW. You put a 1 MVA inverter. 750 kWh is a maximum thing, so 1 MVA. So you oversize the inverter to, so you get extra 250 square root of whatever the algebraic addition, but you get a roughly 30% of the reactive power extra from the inverter which is sitting at that point, and then you can manage that voltage at that point. So all the PV curtailment that the utility in the US were doing, they stopped because of this just inverter sitting there. They could push all the, because you have a reactive power buffer. So nobody said that the inverter has to be exactly the same as the photovoltaics. Of course, money-wise, we want to make it safe, but you, and it's economy of scale, right? If you have a box sitting there and if you scale it up a little bit, you're not losing a lot of money by scaling from 750 to 1 megawatt, rather than putting another 250 box there and then installation and stuff like that. So all these things can be kind of managed if you think through physically and then understand the physical science, right? So how to balance. Okay, good. All good. Coming back finally to objective function. Objective function, network loss minimization, minimizing cost for the minimum cost minimization for the DERs, optimal sizing and placement of DER, which is, like I said, not a lot of value, but you can still try do it and see what are the best place. Maximum voltage stability margin. Let's see an example with loss minimization. So how do you represent an objective function for a loss minimization problem?
Like this.
Maximum voltage stability margin.
Yeah. All that who on the placement.
So there is a very interesting question. So optimal placement is an optimization problem. And what optimal placement does is optimal placement will give you what is the best place to locate a device in an electric grid, considering the voltage and considering the what you want to do with the device, like maximum power. For example, DER, your best location will be that location where your voltage is very strong, not changing a lot. So you can get maximum power from the DER. So that is basically the optimal location problem. Optimal placement and optimal location problem is not very realistic, because if you want to get the PV farm located, and mathematically it says that it has to be on the top of a building, and if it is a large PV farm on top of a building, you cannot just do that. Or let's assume that government decided that I'm going to have a PV farm in somewhere in Gujarat and some other place, and that is not an optimal location. You still have to do it because it's decided by policymakers and decided by government. So optimal placement and optimal location problem doesn't have a, it's very loose as with respect to what you can do in real life, because it's not possible to do these things in real life. But that problem has a validity. Now, how do you make sure that it is possible to do it in real life and also problem has a validity? I feel this is what we can do. You find out what are the optimal places that it can work. So you know these are the best places that it can work. Now you look at what the policymaker or government wants. So this is a place. Now you find out to see what is the margin for the stability or reliability of the system if you, instead of placing here, if you place here. Then you find out measures to overcome that and tell back to the government that, well, if you want to place here, well, it's fine, I'm good, but it cost you 200,000, whatever, So that cost you can get it from this kind of methods that we work on. Otherwise, you don't have a, so the government may come back, yeah, you said that is better than this. How much better? You cannot quantify. You just say, okay, something better, so nobody will really appreciate that. So for that purpose, you still can do the optimization problem. Not very probably realistic, but if you or anybody is trying to do a optimal placement problem, this is what you should be talking about in that paper or in that publication. Otherwise, optimal placement, whether it is a PV or any other thing. So you understood that context, right? So that's basically what we call that as this. So this is kind of related. You can actually try to find out what is a stability margin. We call it stability margin. Sometimes you think it's very mathematical. Really, it's not that mathematical. If you think about just the stability, you can find out the differences in that. Good. So now let's look at a little bit going down. Okay, so we talked about the story. We are now going into the nuts and bolts. Let's see, how do you really do it? For one example, let's see how this has been done. So now we are going to look at a problem, one specific problem of objective function minimization for loss. Okay, so what is the problem? The problem is to reduce the loss on these lines. Okay, how do you reduce the loss on this? What is the loss on a line? Loss on a line is considered active power loss. Oh, by the way, all this power market is, or electricity market is generally called capacity market, which means you only get money for real power. You don't have any, there is no market for reactive power. Even though reactive power is the one which maintains the real power, nobody care about reactive power. So real power flowing through a line is basically what you want to reduce losses of that, right? So real power can be represented as a real part of this equation for as a P loss. Okay, so what is the real part of the I square Z? Real part of I square Z is I square R. I square R is considered as now total real power loss. Or you say all these parts to add together, you get the real power loss. Real power loss is ZJK, real JK, KL, and KM. Why you don't do a real power loss here? Why you don't do any calculate? Oh, in this one there's only 3 terms. You have 1, 2, 3, 4 branches. Only 3 terms. Why you don't have the first branch? There is no line connected. What is connected there? Transformer. It's a transformer connected on that branch, not line connected. So transformer, we don't look at the losses because transformer is considered as a very high, even the distribution transformer can be low with respect to efficiency. I think 85%, 89% is distribution transformer. Sometimes can be higher power transformer is 99%. You don't find the losses inside or reduce the losses inside the transformer, which is not possible, but you can reduce the losses through the line. That's the difference between computer science and power. I saw your face, you're like, oh, okay, that's so we need you or you need us. Solve. Correct. There is no, exactly. There is nothing there connected. That's a transformer connected. And why we call that still I and J? Because you need to have a voltage on the road side of the transformer and on the source side of the transformer. So you take that and then you call it right. There's no line connected, so you don't really worry about it. So you can actually define specific level objectives such as loss minimization, minimum PV curtailment. So this is how you cast for the objective function for a specific problem. For the voltage, you do this, and the constraints, inequality, and the power balance constraint. Right. So all these equations you write. So we'll try to write these equations in MATLAB or in some script, and then you'll be able to solve, and then you'll see how that goes. So what are the putting it all together? This is slide is self-explanatory. You'll understand all the boxes here. You understand this, right? You understand this, right? You understand the power balance, right? You understand the reactive power. You understand the voltage, and this is what we call it as variable definition. And if we did not do this, this is minimizing the total power. So what we did, we talked about optimal power flow. We talked about the how to do an optimal power flow. What are the difference between power flow and optimal power flow? We talked about the pieces of optimal power flow. We talked about how the optimal power flow problem can be casted, and we actually put one specific example of optimal power flow problem for power distribution network, considering minimizing the losses. Can you do the same thing for power transmission network? Yes, you could do the same thing for power. Okay, now we will just expand our knowledge a little bit. Oh, so what is going to change if you want to do optimal power flow for different objectives? Only thing what is going to change is the objective function. The constraint remains the same. Oh, for a specific network. If you change the network to another network, if you change the network to different DER, it's different. So now you can actually do this for any objective function. Okay, so let's look at how the math or equations transpires into other objective function. If you are doing loss minimization, this is what we did. You understand this, right? If you are doing conservation voltage reduction, you are looking at the real part of the reactive power in that network and try to reduce that for the substation bus, considering the substation bus. So you are actually looking at how much power that is coming out from the substation bus. To reduce that power from the substation bus, what will be the voltages on the network? Okay? Because at the end of the day, you want to reduce the power coming from the transmission network to the electric distribution feeder. If you reduce that power, you will get the cost. So to operate an electric distribution feeder, what will be the power on substation bus is what you are trying to find out. After you do that, you will get voltages for the required voltages for the LTC on the source side. So you can tap and you can make sure all the voltages on this can be. Minimizing PV curtailment. What will you do? You minimize the maximum power from the PV, which is maximum power point tracking, and the current power. So if everything is perfect, this minimal value will be 0, which means the power from the PV farm will be the same as the maximum power. PDG is the power coming from the PV farm. So let's assume power coming from the PV farm is 30. Maximum power you can get is 30. So 30 minus 30 is 0. That's the minimum, that's the best which you can get. Power from the PV farm is 25. Maximum you can get is 30. That's 5. You want to minimize the 5. I mean, you want to make it that go down to 0. That's basically your objective function. The last is voltage. These three problems are possible. This problem is mathematically challenging. And what is that? We call it voltage deviation minimization. Voltage deviation minimization is a set point of the voltage with respect to the actual voltages on the field. That problem is not, it's difficult. What else we have? Oh, another important problem of this decision variable. This decision variable is a set point that goes to the controller. Okay. There are actually 3 types of controllers. I don't know whether you know these or not. One controller is operating continuously with respect to the set point. Here we call it continuous operation of the output. It can be done in discrete form or in continuous form, but it's continuous operation output. Second type of a controller is called on-off controller, where you get a decision which is binary in nature, or 0 or 1. Third type of controller is changing set points in percentage, 50%, 100%, 30%. Such controllers are generally called as discrete set point controllers. So this is a general form. The discrete set point controllers is also in the control theory world called regulators. So if you wanted to regulate a water in a tank, it's a regulator. What a regulator does, it actually looks at the level and then it goes to that level. Continuous set point controllers are generally called tracking. So for example, machines, you don't do regulation. You track the, whatever, speed or, so okay, so dynamic, and you see how, so tracking is a big deal, meaning it's not that easy to do the tracking, you have that. And the on-off controller, you say, oh, turn it on or turn it off. So the decision variable that is coming out is generally represented in the form of binary for these 3 devices and smart inverter in some of country. You understand this device? You understand this device too? Right? Voltage regulator. This is called a switch. Switch is actually a small brother of a breaker. Okay, and what is the difference between a switch and the breaker? Breaker is controlled, is operated by a relay or some other devices. Switch is mostly uncontrolled. It opens and closes depending upon manually or automated, but it is not controlled based on some values or changing. That's basically thing. And the breaker also has another feature, which is most of the breakers will have a way to get rid of the arc, and it's called arc quenching media or whatever you call it. And in the switch, you generally don't have that. It flashes and that will go. So you'll have switches, which is a lighter version of a real breaker deployed on the electric distribution system. There are a lot of switches deployed. So you can open and close the switch depending upon a binary variable. So now I will talk about methods of optimization. Okay. So we did, everything is good. How do you solve it? You solve it using mathematical optimization solver that you borrow from mathematicians. Okay? And you don't. So there are different types solvers. Let's assume that you put all these problems that you write in the form of a linear equation. You can use linear solvers to solve linear equations. Such linear solvers that is used to solve linear equations are generally called linear programming solvers. So one way to solve an optimization problem is through linear programming. It's also called LP. Unfortunately, electric grid power problem, when you write a power equation, it is non-linear. Why it is non-linear? Because you have voltage divided V square divided by R, fundamental thing as far as power is concerned. For a current and voltage is not a problem. So this can only be solved through solvers which are not linear, which are non-linear. Such solvers are called NLP solvers, or non-linear programming solvers. So we learned about LP, we learned about NLP. Can you cast this problem as a linear program? Yes, you can cast this problem as linear programming, reducing the non-linear part and call that as a linear. So you can do LP or you can do NLP, right? You can only do LP and NLP if the decision variable that you are coming out is continuous in nature. If the decision variable is binary, for each of those binary state, you have to do the optimization problem separately. So you have to look at each state and then do optimization. Every state is also unknown. What state you want to put is also. So you have to solve this through integer programming to get the binary state, and linear or non-linear programming to get the other devices. So it will be mixed integer linear programming or mixed integer non-linear programming. So now you know what this means. So ideally, a optimal power flow problem is non-linear in nature. If you have a decision variable which is binary, like a capacitor or something, then you must use mixed integer non-linear programming. Unfortunately, this is one of the hardest problem to solve in optimization world. So this is a problem for the So what I'm going to do is I'm going to stop here, and then I will need some time to continue on the next lecture. Any questions? 2 minutes. Next lecture is going to be talking about the linear programming, non-linear programming, and the optimal power flow to solve this. It's good? Questions? Any questions? Are you understanding? All right. And I'm going to continue without any thought. My task for this GAN course is a little tough here, because I am asked to talk about one type of method, solve this optimization problem called convex optimization. So convex modeling is a way to make it computationally faster, and at the same time making sure that all the parts of the nonlinearity is included. Okay, so that's basically my goal. I don't know how many of you are aware of linear programming, or how many of you are aware of linear programming? Okay, how many of you have solved a problem with the linear program? I have 3 people with me, so that's good. How many of you are aware of nonlinear programming? How many of you have solved a problem with nonlinear programming? So that's one. How many of you are aware of mixed integer linear programming or nonlinear programming? So you will be my friend. You will be able to work with me and then do that. And then after that, convex. So what I will do, I have to stick to my scope, but at the same time, I have to make sure that you understand. So I'm going to scan through some slides and then give you some best judgment of other 2-3 types of programming. Then I'll go to convex optimization and talk to you about how the convex optimization is done. That's basically part of the. What is the other? I was thinking I will continue. I don't know. Anybody wants to have a break? Because it will recoup again, right? Because then it will be, No, it's fine. I will I'll go with the flow. It's I like, but looking at the noise and the disturbance factor comes, because that. So let's see. What we can do is we will try to do it in 1 hour, and then we'll entertain questions. Last 10 minutes will be like discussion questions. So, linear programming, by the way, is uh, pretty much understood, and people understand the linear programming. Linear programming is a characteristics is a well-defined single objective must be stated. There must be alternate course of action. The objective in each of the constraint must be expressed as a linear mathematical function. Okay. Oh, by the way, when you say linear, non-linear, and all that, what does it mean? It means that the objective function, there are two parts in optimization: objective function and constraints. What happens if this objective function is linear, constraints are not linear? You have a challenge because you have to make the constraint linear, right? So people talk about both type. So for example, suppose objective function is quadratic, second order function is quadratic. So you call it objective function quadratic, is called quadratic programming. If the objective function is quadratic and constraint is quadratic, you call QC/QP, quadratic constraint, quadratic programming. To define what are the objective functions and constraints and which linear constraint quadratic programming, LCQP, you will call it linear constraint quadratic. For each of those, solution methods are defined by mathematicians and they solve it. So you will see this term coming to you as constraint, and programming is defined for function, objective function. Constraint is C. Programming is non-linear programming. Non-linear programming is all dependent on function, and the constraints is actually C. So just to give you the jargon, otherwise you'll see hit with these very, I don't know what's going on. Understand, right? Okay. So we just quickly go through this. This is something which is math, but I'll put this slide here, which is important. What is assumptions for linear programming? There should be conditions of certainty to exist. That is, a number in the objective function exists with certainty and not subject to change. Okay. There is an objective function. There is a number inside that objective function. That number is there. It's not moving. If it's moving, then you cannot get this. You cannot find it. Linear proportionality, linear additivity, divisibility, non-negativity. These are some mathematical aspect for linear programming. So LP problem in standard form looks like this. Okay, this is objective function. See this objective function here, C times X. It's not X times X. C is basically what you call it as a constant that you are representing multiplied with X, which is mx plus b form. Linear iteration, linear iteration and linear optimization. Linear iteration, regression. No. I'll have to explain a little bit. So there is something called so there are three words. Okay, I'm just putting three words. One word is called approximation. Okay? Approximation, you know what approximation. So you have an ax square plus bx plus c, and I say that ax square is not required. Bx plus c I used. This is approximation. Okay? Instead of approximation, I do aggregation. Ax square plus bx plus c. And I'm going to say that ax square will give bx plus c will be added together and call it c square x plus m. This is aggregation. Okay. Third one is something called relaxation. I'm going to say ax square plus bx plus c. I cannot solve this. I do ax square as am plus bx plus c. Now m is x square. I know that on the back of my head. I'm not going to say that to the solver. When I trick the solver, am plus bx plus c. Somehow where to find the solution. Now I take this m and I try to find what is x from the m. So I'm not losing anything. I'm relaxing some. I cannot find x. I'm in trouble from m. That's my problem. If I can find x, then I'm a brainer. People will say, oh, I get the exact value of x without losing it. Three different. Regression is a process of optimization. We're not optimizing anything. Regression is a process of, all these things are not optimization. Relaxation, approximation, and aggregation is not optimization. It's a way to reduce the complexity of the problem and how to work with the problem. That's all. Okay? Regression is a process of trying to what? What is regress means? Regression is a process of trying to come up with the best fit on a specific equation and find out what is the best fit on the equation. So you're not approximating, you're not relaxing, you're not aggregating. The closest will be probably you can say aggregation, but you're not really aggregating and you're finding out the best. So that now you understand the difference. So that today now convex optimization uses this interesting concept of relaxation. So that is why I'll come to that and then I'll say how to, we call it recasting the problem. Casting. So I use the word casting. Recasting. You can recast multiple times and I'll get something very clean. But inside that, there will be a lot of dirty stuff which I need to unwind, which I'll do it later. That's basically what is called as convex optimization. But, so you understand the difference, right? So, by the way, so this is the LP problem. If xn satisfies all the constraints, then it is a feasible. Feasible solution maximize the objective function is called the optimal solution. Okay, so you see feasibility and optimal value. Can I move a little bit faster because we are working on convex optimization? Is it understood? So then you have for the linear programming, what you generally do is you try to add two new variables on the existing framework and trick the system. These variables are called slack variables and surplus variables. Slack variables is added to A when the A is less than or equal to constraint to convert that into equality. So if something is less than or equal to constraint, then you make it equal by adding this slack variable, right? And why I want to make it equal? Well, then only I can work with linear programming. I cannot work with linear without that. And if you have another way, I'm surplus. So then you do two different methods in mathematics. One method is called graphic approach. It's restricted to two decision variable. The second method is called simplex algorithm. It's used by a matrix operation. Oh, by the way, this is interesting. Cxj is equal to m. What is x? M divided by c. You see? Now x is a column vector. C is a matrix. C times x is equal to m, column vector. What is x? C inverse of m. See? That means just by matrix inversion, you can get the solution. That's the method of linear programming. So here is a graphic approach. Some examples here. Special cases, you can just skip that. And these are solutions, bounded solutions and unbounded solution. In a simplex method, you will make a table and you try to put the variables. These are in the books, by the way. So you can take it from the books and then understand how it's been done. I'm not explaining that. Everybody might have done one part in simplex. You make the steps and then you try to reduce with, these are the variables that you're adding. And by the variables, you try to make the table and reduce the table step by step, and then you can reduce. I just breezed through. It's okay, right? It's math, first you can read. Good? Okay. NLP. This is the forms for nonlinear programming, and this form you already have seen. In the nonlinear programming, these variables are all nonlinear in nature. So you see f of x, g of x, h of x, right? Scalar objective function, n variables vector, inequality constraint with m vector, m equality constraints. M eq is basically the vector for that. Sufficient condition for a unique solution is f of x must be convex and a feasible region must be convex. Do you know in the math the convex functions and concave functions? How many of you heard of convex functions? I have to move on the screen. I can do this one after. This is a simple representation of a convex function and a convex. So if you have a ball, a closed loop ball, you have a stable point, you go to the ball and then sit there and then you can find the minimum value. And if you're finding this is actually close to this, exactly this point, this is probably your optimal point. Okay. That optimal point, if the, oh, by the way, minimization problem. If the minimum point or minimization problem becomes 0, what does it mean? That's the best scenario. So for example, PV power coming out, cut maximum power minus the actual power is 0, which is the maximum power function. That is basically the best. So your goal is to reach here. Again, why you cannot reach there? Because of constraints and because of the problems challenging, you cannot reach that point. That is why we use optimization with, we call it minimum. Okay. If you are doing in the form the same thing as a control and cast this as an error, and that error becomes 0, that's the control. So that means you have a control taken care of. Controllers are basically one input, one output. What happens? Multiple input, multiple output controls or multi-variable controls is going to be challenging. You cannot just get that. So if you are going to minimize that problem, oh, can you find the maximum and find the inverse of this? So you can take that same function, flip it backward, and then find the maximum point. That's also good. So many times optimization folks, oh, by the way, what I got an optimization problem, results made, decision coming out. How do you know that's good or not? Challenge, right? Because it's a optimization done and it's almost like a wish list. Oh, I have a goal to make it. Yes, if it is a photovoltaic curtailing, I can know it's good or not. I can match with the maximum power. Some objective is not possible. So you know what optimization folks does mathematically? They will invert the problem and find the maximum point. And you find the difference between this. It's called gap or optimal gap. The best point is when there is no gap. They hit with each other, which means optimization is solved properly and there is no gap. No gap doesn't mean that it is it is going to 0. Minimum value, it may be sitting at 3, maybe sitting at 4, but no gap, no? Which means, it may be, what I mean by that is, this line may be here. That is also, it's a gap, okay? So, this is how you work with optimization. So, any optimization problem, you can get a feasible solution or a good solution if the curve is like this. If it is like this, it's hard to get the minimum value or a minimum solution or a feasible solution. So there is a condition in every time. You say in optimization world, that the objective function has to be in a convex form. Now, what happens if you get an objective function in the concave form? You recast that problem and bring into a convex form and then solve it and then do your things later. So gx is all, I mean fx is convex, gx is all convex, and hx is linear. Except in some cases, there's no guarantee that local. Oh, by the way, if you have a point, I want to mention this also. This point that you reach in this function is the best point, right? What happened if you, the optimization solver, found this as an optimal solution? And you are here. Yeah, I mean, this is optimal. I agree with that. This is also optimal. Yeah, I agree with that. So everything other than this is all optimal. But there is only one point which is the best. And that point is called global optimal. Globally optimal. Okay? So for example, this is a nice curve. What happens if you have something like this? This is also convex. Weird convex. So you have optimal point here, optimal point here, optimal point here, right? So all the other points which are not globally optimal are called local optimal. Okay. So you see something what you see here, local optimal. Okay. So there is no, except in special case, no guarantee that local optimal is global if sufficient conditions are met. So then there is another term in optimization world, people call that sufficient condition. Okay. There are two words, sufficient condition and necessary condition. Okay. Do you know the difference between those two? Necessary conditions are obviously necessary. You must have that condition taken care of. Sufficient condition means at least these conditions are good enough to find a solution for the problem. Other condition, even if it is not there, you still can find a problem. Right? So the local optimal point is global if sufficient conditions are. If sufficient conditions are violated, what happens? Obviously, you would not get the results which are going to be optimal. Yeah, some graphs there to talk about linear programming. Another thing which I wanted to talk about is some two other things comes in math uh, uh, called definite matrix. Have you heard of positive definite? Okay. Negative definite. So positive definite conditions are basically required to develop any problem, even just even if instability problem. Every time you need to have a positive definite condition. So having said that, positive definite. Oh, have you heard of semi-definite? Positive semi-definite. Okay. I don't have to explain, right? You understand. One is greater than 0, one is greater than or equal to 0, and there are some sufficient condition when mathematics they are developed. I'm not going to talk about that. There is something called KKT, Kush-Kentucker conditions, which is developed for working. Now we go to quadratic program. Quadratic programming is represented in this form, okay, which is A transpose x plus 1/2 x transpose bx. You see, this is linear. This part is non-linear. Can you see that? Why that is non-linear? Because x transpose times x. You are actually square. So you can be solved using LP techniques by reducing this to the LP, and you have some condition that B has to be positive definite. Then QP solution is unique. If B is positive semi-definite, optimum value is unique, and there are some requirements. These are classically solved by people, so it is there in the books and things like that. So here is a representation of quadratic programming in using LP. You can solve that using one way to use a quadratic programming using LP. How do you solve it? So this is actually classically done in economic dispatch. Have you heard of? Have you done any course on power system operation and control? Yes. Have you heard of economic dispatch? economic dispatch, you have a cost function for generator represented in the quadratic form. Okay, what is the way to solve that quadratic form function without using quadratic programming? You know what you do? You take a derivative of the quadratic function. You take a derivative of the quadratic function, then it will become linear function, and you equate that to 0. Oh, by the way, if you, I think this is probably known to you, but I don't know whether you know it. What is this point? What is the derivative of this function at this point? So you take a derivative of the quadratic function, equate that to 0. This is what we do in economic dispatch for a cost function for a generator. Economic dispatch is not optimal power flow. You can extend that to optimal power flow, but you can put the generator cost function. So that's one way you can do. You will see something is written in that form, and correct programming can be used. Another way of writing the quadratic programming is through quadratic programming in with respect to time, multiple times. It's called sequential quadratic, programming. Again, I'm not going to go through this. Let's skip the algorithm. So some examples that we did. One of our tests here on comparing sequential quadratic programming with nonlinear programming, finding out the voltage profile on a system, and then checking it out. And the transmission network related results. So these are some of the basics of. I will start with convex optimization. Here is an optimization, real optimization problem. This is a network, a real feeder, which is unbalanced, which has 9,500 single phase nodes, 107 switches, 1,275 single phase nodes, 354 single phase PVs, and then DGs and storage. So if you want to really work on a field-like problem, you can see the number of variables and the decision variables and things like that really work on. So that's a very important question. So it can exponentially increase to 315 minutes, 500 minutes, 700 minutes, 800 minutes, that kind of number. So what you do is no optimization problems you can solve without divide and conquer. So you try to divide and conquer. So one of the approach that is used in the field is to using parallel computing. So you run it on GPUs, and parallel computing where all the knowledge on software and other things will come into place. And there are high performance computing infrastructure, HPCs, used for solving this kind of optimization. One of the fascinating part of this optimization world is that everything is directly related to cost. So there is a direct deliverable sitting there, except for it's investment wise it's there, and then people like it to do. Some of the utilities. So for example, system operator in the US run the optimal power flow every 10 minutes for 30,000 bus of electricity. They invest it on the, because that's a value. That's a lot of generator using of generator, cost associated with how generator should change with respect to time, what power it should come, especially with renewable, is generally called as resource mix. Resource mix means when the renewable comes in there, there is a dip in generation in in nighttime, and then high peak in generation. So this dip and peak, if you have generation dip and peak, somebody has to sit there and compensate for that. So the gas turbines and other folks are sitting there and trying to, they call it ramping up and ramping down. So this goes up and down, goes up and down all the time. So if you want to find out what is the best resource allocation, one gas, one nuclear, one hydro, one renewable, this is a problem that is a future problem because people don't know. In the conventional olden times, you don't care about all this and you put the stuff in. When renewable comes in here, so that affects the optimization world, that affects the electricity market or capacity market. So the problem is complex, but methods to solve this problem, if somebody can do it realistically, utility likes it. But there are a lot of mathematicians and people like us solving it without not real, so like mathematically you can solve something, but they come up with a solution. So there was one paper which you were reviewing, it says there is a solution. Yeah, you can put that, and you put a solid state transformer is a head of solid that in one location, and then everything works well. Solid state transformer is technology is not even mature, and you cannot even buy that box, but that's a math world. So there are folks who does both. Just giving you some stories because it's a very interesting, so algorithms that has to be scalable. Otherwise, you cannot do anything. That's the whole thing. So now we will talk about convex optimization. So this is an example of approximation and relaxation. So what are we doing in approximation? We are cutting some things. Okay. So you see right here in the approximation, what we are doing is we are approximating this whole thing and this box. Now let's assume that you don't cut. You put everything in the form of a bucket like this. Okay. You are okay. But if you do that, you will have a lot of space here. You may get into this point as an optimal solution. It's not feasible. You may get into this point as an optimal solution, which is not global. So this is the challenge with respect to approximation. Instead of approximation, if you relax, what are we doing? We are extending the space and to cover everything in a bucket. So you are now, the only challenge is you have to find it here in the green area. If you find it somewhere else, you are gone, right? So this is the difference between approximation and relaxation. Make sense? So there are different category of convex optimal power flow models. Okay, one type of convex optimal power flow model are based on voltages on a bus. Okay, and power injected on a bus. Okay, this is done through solving node voltage analysis, basically. So those node voltage analysis, when you solve it, you will not have any current flowing through the line, but you convert all the current variable in terms of voltage and you solve for voltage. So this is what you do for voltage based studies. Such models are called BIM, bus injection model. Bus, remember bus injection model. Okay. Another model is, okay, I don't worry about voltage, I only worry about current. So you recast the whole problem in the form of current. When you are looking at a current, you don't look at the bus, you look at the branch, because current is flowing through 2 points as a branch. Okay, such models are called branch flow model. Okay, so there are two types of models in OPF: bus injection models and branch flow models. These injection models are very useful for, we already know the story. Bus injection models are very useful for transmission networks. Branch flow models are very useful for distribution networks. So you can categorize them and put it together. If you do both of them together, it's a different deal. But you can actually use these two models. Now there are mainly two different forms of matured optimal power flow problems using convex optimization. One method is from mathematics that we borrow is called SOCP. Okay, SOCP is represented for second order cone programming. Okay, so what you do is you write this whole relaxation space in the form of a cone, and if you put it in the form of a cone, it's basically a structure that you can derive linearized forms from that cone. Okay, so cone can be written, equations for the cone can be written nicely in the form of a form. So it is obviously coming from what you call second order cone programming. The other type of convex optimization runs into a group called SDP, semi-definite programming. Semi-definite programming, you know what a semi-definite means. So basically two different type of OPF, and there are methods to relax the problem. Is one of the method that is used for relaxing the problem is a method developed by McCormick. It's called McCormick relaxation. Okay, so we are going to discuss comparisons between semi-definite program relaxation, second order cone program relaxation, and linear AC problem formulation. So here is our problem. We casted this problem again. Everybody understand these three equations? Yes or no? Yes, we have objective function, equality constraint, inequality constraint. So to model in a linear programming, this condition should be f of x should be linear in x and u. G of x is a affine function of x and u. What is affine means? Affine means linear. What is linear function of f and u? Affine function of f and u, what is the difference? In the affine function, your conditions can be non-linear, but the functions has to be formed in the casted in the form of linear. Okay? That's the difference between linearity and affine. And f of x should be an affine function. So, for example, power flow constraint corresponding to equality constraint, and they are non-linear in nature, but you can be recasted in the form of a affine thing. So, let's look at the power flow equation. This is the power flow equation. You remember this? This is called, what equation is this? Voltage drop. This is the power balance. This is the apparent power equation. Now let's multiply both the sides by equation by their Hermitian transpose. You know Hermitian matrix? It's a little bit of math here. Let's say there is a matrix called Hermitian matrix. I'll talk about Hermitian matrix later. So if you take a Hermitian matrix and you multiply this Hermitian transpose, what we are doing is you are multiplying this Hermitian transpose. You are multiplying this right here and then this here. So you will can cast this whole thing in the form of this. You agree with that? Can you see this is this? Okay, how do you see that? Not a big deal. Can you see this? You cross multiply and you should be able to get it. Right? I'm not doing the math in here, but you can check. So, what are the nonlinear type of parts in the power flow equation? You see this equation when you look at in the back right here. What is a nonlinear part in that equation? You see right here, this is S, Z, ZS, and Z, L, Z. This L is actually what we are writing here is I, J, I, H is written as L, right? So you see this is the one that is introducing the nonlinearity. Are you following? Right? Any square term that is introduces the nonlinearity. So this term and this term introduces, these two terms are not introducing the nonlinearity as such as the problem is concerned. So what do you do? What is the easy way? Whatever is introducing non-linearity, cut it out. Okay. If you cut it out, this becomes linear. Yes. Do you have a method to solve it? Yes. What are we losing? What is this? I square times Z, right? What is that? We are ignoring from voltage drop, ignoring the effect of power loss term on the voltage drop. Okay. The effect of power flow is still included. Power flow is happening, but power loss term is neglected. From power balance, we are ignoring the power loss term, basically. Okay. What happens if you ignore the power loss term? Will you be able to solve the power flow? Yes, you will also. What happens if the loss is not included? Well, if the loss is not included, you will lose the value of the loss or whatever cost which you want to. Okay, so linearize, approximate, actually write this part equation. This right here is the same as this. You can see that part of that equation, and then you can solve for the power and we can imaginary part, two-part, linear in state for the P regions. All are linear. See, they're all linear. You can the system. This is called underdetermined system. We are not doing. You can solve that math with approximations, and you can actually utilize get the solution. So our system. This is our small system. And balance equation. This is the power flow. Oh, by the way, when you solve for a system, you will be looking at the optimal power flow. So this is a voltage that optimal power flow. Voltage that comes from the power flow. The voltage is different. We are reducing the loss term in this. It remains the same. You see, so you have to. Okay, good. Now we're going with the convex optimization technique. About key aspects on the convex optimization technique. One method of convex optimization, right? So SDP, you can represent this in the form less than or equal to B, and with what you call as trace. Trace matrix, how to find the trace value for that. Okay. So you see this here, a ZZ nonlinear, right? IIZ. What we did, we tricked it. We tricked the math for a computer. It L. So this II becomes L. I made that II is I square into a new variable. The computer thinks it's linear. So that this becomes right here. This becomes right here. Now you look at find out the rank, whether the rank of the matrix is good. If the rank is 1, drop the rank constraint, make the problem this rank equal to 1. Drop the constraint. That is called what we call as relaxation. Now, you can solve it. So with our same 5 examples, this is the rank for each of those. After you find the power flow equation for each of the buses, you write, and we relax the projecting the voltage and current variable to a higher dimension, and the non-convex you are dropping to achieve the relaxation. Equal to 1, the solution is not feasible. If after solving the rank is equal to 1, solution. So you can actually use that for if you are going to represent this of second order cone programming, you will cast these power equations like this. Okay, this power equation has a very nice feature that is much like a cone. So the cone equation has got a cone definition is coming from a circle at the base. So when you have a circle equation, you know that x square plus y square is equal to m or c. That's a circle form. So this is actually a kind of circle, but you can relax that as a second order quadratic inequality in the form of a cone. So if you look at this is non-convex. You agree with that? Because you have square term, right? It's non-convex. But you put that in the form of this inequality. So if you put this in the inequality, then it will relax in the form of a cone. So that is basically the cone function. Now the solution, so this is like what we have for the cone function. And if you have a cone function solution, you can actually look at this cone function and you can solve that cone equation with the help of a solution for cone. So there is a classical representation of how to solve a cone function and utilize the cone function. So if you do that, then you will be able to get a feasible output solution. And here is an example with 5 PV located on a part of an electric grid, and you can actually utilize to run the cone programming. So basically, I'll stop right here, and maybe we can, after lunch or some, we can do some small examples for test.
Thank you, sir, for that insightful session. I hope all of you
Oh.
enjoy the session.
I know you are
If you have any queries, please ask.
yeah.
If you have any queries, please ask.
We are almost done with the time, but anybody has any questions? Of course, no questions because we can have lunch or too hard or whatever. But anything that comes in your mind. This time I pulled my time. I made sure I gave only the essence one, not the non-essential. I mean, there are, I don't want to say non-essential. There are great mathematics part there, but I try to keep the right. Is okay, right? That level. I don't want to go to the
mathematics as well as
yeah. And then they can work on it, and then they have to do it separately. But I gave you the real part pieces that is to it.
Thank you, sir. Now we have the tea break outside the seminar hall. Please have a tea. Okay, and all of you request please assemble at 11:45.